Hi, and welcome to another lesson in the physics video series. Today we will be discussing pendulum restoring force and energy conservation. This is a very similar concept to the previous video where we studied simple harmonic motion for a mass vibrating on a spring. Well, it turns out that in a case of a pendulum, the mass, which is swinging back and forth past the equilibrium position line, acts exactly the same way as that vibrating mass on a spring. That's called simple harmonic motion. All right, let's get started. Before we can discuss any of the specifics about a pendulum, we first have to show you what a pendulum is and how it works. So a pendulum is very simple. It is a mass on the end of a string that is allowed to swing from a point somewhere above it here. Let me demonstrate. If I pull this mass off to the side a certain number of degrees, as you can see here, these blue tick marks measured what was 26 degrees. If I hit play, the pendulum goes into oscillation. This is simple harmonic motion. We're going to explain this in a lot of detail in just a moment. But very simply, this is what a pendulum is. It is a swinging mass that's swinging back and forth, and we will be interested to see the variations that come with a changing length and a changing mass. Now that we've given you a brief introduction to what a pendulum is and what it looks like when it's swinging back and forth, let's look at this static diagram and take a look at all the parts of a pendulum. As we said before, we have a mass on a string. The string's length is letter L, and when the mass is hanging straight down with gravity, that is the equilibrium position. That is the place that the mass wants to be. But if you pull the mass to the side, left or right, at any angle, theta, then you immediately set up an unbalanced force which wants to pull the mass back towards the center. So when we discuss these forces, we have to look right here at this vector diagram. Let's discuss that now. To understand these green and blue forces, we first have to recall that the weight of an object always points downward in the vertical direction. And since this string is under tension, we also know that there is something happening along the string, and we know that there's something happening to the side of the string which causes the mass to return to the center. So let's take a look at this part of the diagram here, and we're going to break down vectors. We're going to resolve vectors, just like we did way back at the beginning of the curriculum. Since the mass is pointing straight down and the string is making this angle to the vertical theta, we can take this weight and we can resolve it into two components. One that is perpendicular to the string and one that is parallel to the string. The first component, which is the green one, is the restoring force. Since this green component is dependent on the angle, it is the opposite of this theta right here that is related to the sine of the angle. So the restoring force, which pulls the mass back towards the equilibrium position, is equal to mg sine theta. And so the weight force, which is at an angle to this string, can also be resolved into a component that is parallel to the string. The restoring force, as you recall, was perpendicular to the string, but now this blue force is parallel to the string or adjacent to the angle, and that is equal to mg cosine theta. But the question is, what is this blue force? Well, it turns out that the tension in the string, which is keeping the mass in the arc, has to be pulling towards the center. That's really a centripetal force. The centripetal force that holds a mass on a string while it swings in an arc is centripetal force. So the force of tension, T, is equal and opposite to the vector component of the weight at the angle theta along the string. So what we're saying here is that the perpendicular force to the string, which is the restoring force, mg sine theta, and the parallel force along the string, which is the tension, these actually change in magnitude because of the angle. As the angle changes, the values of the restoring force and the tension also change. Hopefully you can see that as this angle decreases and the mass returns towards the equilibrium position, the sine of the angle, sine of 0, is 0, and there is no restoring force at this point, meaning there's no force pulling it to the side to bring it back to the middle because it's already there. And the tension force at mg cosine 0 becomes the full weight of the object when you're at position C, the equilibrium position. But then as you swing through the arc, these vectors reverse themselves, and the restoring force grows and tries to pull it back towards the center, and eventually it causes it to stop at some high point, maximum H over here. And then of course the tension is also reduced correspondingly, and then the process repeats itself and will tick-tock indefinitely, going back and forth if there is no friction loss at the hinge up here. Let's take a look at the changing restoring force vector in the simulation. If I pull the pendulum so many degrees offset, I'll make it 25 for this example, and then I let it go, you're going to see the green vector. Even though it says that this is the velocity vector, it can also represent, in our case, the restoring force. And the restoring force changes direction and magnitude. That's why the length of the arrow is growing and shrinking. Let's look at it in slow motion. As we pass and we go to the high point, you can see that the velocity is 0, and the restoring force would have to be at its maximum. And then as we swing through and we come to the bottom, we will see that our velocity is in fact maximum. The restoring force would then be minimum. It would be 0. And then as we continued up the arc, the velocity would decrease and the restoring force would increase. And as it pulls against it, that's what decelerates the mass and slows it down as it stops at the highest point in the arc. Now that we discussed the vectors for restoring force and the tension, let's take a look at the potential and kinetic energies respectively. When the mass is at point A, which is a maximum height above this baseline, which is the lowest gravitational position, you can see that if you just lifted this mass straight up, you would have a PE equal to mgh. H is a non-zero value, so you have some invested energy, and this energy that is stored in the mass will cause it to accelerate and convert from potential into kinetic energy. So at point A, we have the maximum potential energy and the minimum kinetic energy. You can see that because the mass is not moving, so there would be no kinetic energy. As the mass swings through its arc and goes towards the equilibrium position, the energies exchange. The potential feeds the kinetic. So the kinetic increases because the potential decreases. And then when you reach the lowest point, C, you have no more potential energy. You have no height. So you have converted all of it into kinetic. And of course, the mass has momentum and inertia and continues to swing past the equilibrium position. And as it ascends, it goes back towards the height it started from, which is now level B. You can see once again that the kinetic feeds the potential, and the potential energy increases because the kinetic energy decreases. And then this returns, and the process continues indefinitely when there's no friction. Let's take a look at that in the simulation. Here we are back at the simulation. I draw your attention to the energy graph, and we're going to look at the energy bars. And we have the green bar for kinetic, the blue bar for potential. The total energy, as you remember from the other lessons on energy conservation, is that it is the same. PE plus KE always equals the total energy. So this will not be affected. Of course, if there was friction, then we would be losing energy. But we're keeping it in a frictionless environment right now. So as I start the simulation, I'm going to run it in slow motion so you can look at the bars. The PE is decreasing and the KE has increased. And as we get to the very base, here's the equilibrium position. The PE is fed into the KE. PE is depleted. KE is at its maximum. The inertia causes this mass to continue swinging. That's why you have the green velocity vector pointing to the right. And then, of course, you see at the ascent, the KE once again reduces to 0 and the PE rises to its maximum value. We will run this in full speed and you can see the constant exchange between PE and KE. So in conclusion, we can summarize that the mass on a string, which is called a pendulum, has two components of the weight, one that is perpendicular to the string, called the restoring force, equal to mg sine theta, and one component that is parallel to the string, which is called mg cosine theta, which is called the tension, mg cosine theta. The restoring force is what pulls the mass back towards the equilibrium position along the arc, and the tension is the centripetal force that keeps the mass in the arc. The pendulum is a conservative energy system, and potential energy converts to kinetic energy and back again as the pendulum swings through its arc from high point to low point to high point and back again. This would go on indefinitely if there was no friction. I hope you enjoyed this video, and I thank you for watching. In the next video, we're going to take a look at the period of the pendulum and spend some more time discussing the factors that affect the rate of oscillation. Okay, we'll see you there.